Hello everyone, my name is Czikhardt and I'd like to present the results of multi-year field tests of compact radar transponders for InSAR Geodesy, which are carried out jointly by Slovak and Delft Universities of Technology. We are testing the first commercially available compact radar transponders, ECRC from Metasensing, and these contain two pairs of receive-transmit antennas for C-band SAR. And their clear advantage compared to large metallic cone reflectors is their small size. However, concerning their use for InSAR, our primary question is, are they a reliable alternative in terms of their radiometry, positioning and phase stability? We perform our experiments at two independent test sites, first in the Netherlands using 2 units installed since June 2019 with nearby 6 reference cone reflectors, and second in Slovakia using also 2 units in very short baseline configuration. We analyze almost 2 years of Sentinel-1 time series from 4 tracks using our dedicated Geodesy toolbox. For the transponders, we observe high average RCS of 40 to 45 dB meter squared, which is comparable to 2 meter large triangular trihedral reflector. However, the temporal RCS variations of transponders are significantly higher than for the corner reflectors, which are under the same clutter conditions. So for example, this small trihedral, which has 10 dB lower RCS, has better RCS standard deviations than the transponders. And as shown in these scatter plots below, of RCS against the measured temperature, this is partially caused by the temperature dependency. So what are the implications on the phase measurements? To test the phase stability of the transponders, we compute double differences for short baselines between transponders and cone reflectors. And this figure shows the phase time series in orange and blue, while a black line is the measured temperature. And the scatter plot shows very clear correlation. And to verify this signal is not coming from the reference reflectors, we also compute double differences between independent reflectors. And as now scatter plot shows no correlation, this is indeed a consequence of temperature dependency. And estimating and removing this temperature dependency resulted in factor 2 improvement of the standard deviations of phase time series, which are now better than 1 millimeter. And from the residuals, we estimate the annual drift, which is below 1 millimeter per year. And it is especially important for long-term InSAR reliability. So computing the double differences between nearby transponders, one would assume the temperature dependency to cancel out. However, some correlation is still apparent, suggesting different scaling factors for different units. We also observe some spikes in the phase time series, for which we found the snow cover to be the possible cause. Finally, to evaluate the SAR positioning accuracy of the transponders, we compute the absolute positioning errors, as the differences between their subpixel positions observed in SAR images and the GNSS-derived positions with reintroduced SAR timing biases. So for the corner reflectors, we achieve average positioning errors of few tens of centimeters, which are very close to Kramer-Rao, given by their signal-to-clutter ratio. However, for transponders, we observe significant range timing biases as a consequence of internal electronic delays. And moreover, these are apparently antenna-specific, as they vary from 1 meter to 2 meters between individual transponders and individual orbits. So to wrap up, although transponder provides a high RCS, it has significantly higher temporal variations than cone reflectors, and one should consider this when computing SCR, which would yield biased phase precision estimates. For precise positioning applications, one needs a calibration of antenna-specific internal delays. One should also account for temperature correlation of phase time series when using transponders for long-term InSAR. One should be careful about the snow cover of the transponders. And for long-term reliability, we estimate the drift of the transponders to be below 1 mm per year. However, this requires longer time series and cross-validation with other groups. So our preliminary conclusion is that compact transponders are indeed a viable corner reflector alternative, but individual calibration is recommended for their precise InSAR applications. Thank you for your attention.